Hey everyone, welcome back to Smart Robots Review, the show that reviews robotics and other fantastic tech from around the world or out of this world. I'm your host Elias, and it's great to have you here as always. Today's episode will feature NASA's RASSOR, R-A-S-S-O-R. This is a very special mining robot designed to operate on the harsh operating environment of the Moon or even Mars. The gentleman speaking is AJ Nick, a senior robotics engineer from NASA's SwampWorks lab located at the Kennedy Space Center in Cape Canaveral, Florida. The SwampWorks team is comprised of physicists, chemists, engineers that are working to design tomorrow's future exploration space tech. If you've been watching this channel, I have interviewed AJ Nick before, and he has given me a lot of great information. He's a very intelligent guy, and here he's talking about RASSOR. So enjoy the interview, and remember to leave thumbs up if you enjoyed the episode, and visit jlcpcb.com for all your PCB prototyping needs. They're a sponsor of my show. I appreciate you guys. Everybody enjoy the show.
So some of the stuff I worked on in the past, I probably worked on this one for over 5 years. It's a robot called RASSOR, and it's an excavation robot. And so this is tied to a mission where it would go before humans, and it would land with a lander, and on that lander is a processing plant. And so that processing plant is meant to take the soil, regolith, the local material on the surface, ingest it, process it out, extract the water, split it into hydrogen, oxygen, store it, have it all ready for when people land. So the lander is the big processing plant, but on that lander would be an excavation robot that deploys. And so that was what is the RASSOR robot that we've been working on. And so one of the challenges with RASSOR, or any excavation tool on the moon, is that you've got two things fighting against you. One, you have to fit on this lander, and as I just mentioned, that lander has massive amounts of other processing and tools and technology on it. So the excavation tool only gets a very small little part of that lander. So we were kind of told as initial guess, you get 50 kilograms. So there you go. You get 50 kilograms and this small volume of space for your excavation robot to fit in on a lander. So how are you going to excavate and collect all the soil you need to successfully make water? So the two parts of that is, one, it already was small, we were only at one portion. The other part is it has to be lightweight because it costs a lot to launch things in rockets. So everything NASA does, they're making things lighter weight and smaller. Then you get to the Moon or Mars and you're in reduced gravity. And you're a sixth of your weight on the Moon and you're a third of your weight on Mars. And so now you've taken something that weighs 100 pounds on the Earth and it weighs like 10 on the Moon, or like, maybe not be the perfect math, but you get the idea. It's a very lightweight vehicle. So when you think about how you excavate with such a light vehicle, it's not really done on Earth. When you think about terrestrial excavation tools, you think of huge, monstrous caterpillar machines, tons of steel. They kind of just throw more steel at them to make them robust, right? Because the whole idea is that they get their traction from their mass, from their weight, and they use that weight to be able to react to the excavating. So when you think of like a plow blade, all the traction to push a plow through the dirt comes from its weight. When you think of a backhoe, as the backhoe scoops through the soil, for the backhoe to actually be able to pull and collect dirt, you have to have that mass holding the excavator in place. So when you now say you only weigh 10 pounds and you're trying to go excavate this soil, that seems like a pretty hard task to actually do it. So that was why we actually originally developed RASSOR. And we kind of attacked it in a couple different ways. There had been a lot of different research over the years about different excavating techniques and things like that. And there was this one study that happened like 10, 15 years ago that was the idea of using a rotary scoop. And the scoops were staggered on it. And the scoops, so each scoop was only a really small size. So as the drum rotated around, each scoop only had to excavate like a really small portion. So now you're reduced, instead of having a scoop that's this wide, you would have a scoop that's this small, so at any time you're only scooping a small amount. Well, we actually did a test to prove that with a lightweight vehicle, even that small little scoop is still too big. If you were to take that small scoop and try to excavate with it with a rover around this size, it actually would just push the robot along. We actually did gravity offloaded tests with a vehicle in the right size, and the robot would just slide across the ground and not be able to excavate. So then what we did is we said, all right, well, now we have these staggered scoops on an excavation tool. What if we place them opposite each other? So now we have a robot with a mobility platform in the middle, wheels in the middle, and then two drums on either side. And so as the drums lower and they start digging the soil, one drum rotates this way, the other drum rotates the opposite way, and they actually cancel each other. And so this drum provides excavation force for the other drum. So now you're actually able to drive while digging, and your actual traction in your wheels have nothing to do with your excavation force. So we've built this twice. We actually built an initial prototype. That was kind of how our group operates. We do quick iterations. We build a quick initial prototype to prove the proof of concept. So we did that. We built one, and we did the gravity offload test, proved that it works, proved that it can excavate with its mass actually offloaded to the lunar gravity, and it did work. The thing about that rover is it weighed 120 kilograms, and it can only excavate around 30 or 40 kilograms total, right? Which isn't terrible, actually, when you think of Caterpillar devices and big things. When you think about how much soil they actually excavate compared to their actual mass, that rover really wasn't that bad. But because of the initial quick proof of concept that we did, we were able to get funding to follow on to what we call Razer 2.0. So, with a continuation of a project, you'd like to think you get more money, and we did. We got a little bit more money, so we were able to iterate on that design. So we went from the 120 kilograms on the first version to 60 kilograms on the next version. So we cut the weight in half. But not only did we cut the weight in half, we were also able to increase the excavation capability. So it actually excavates 96 kilograms while only weighing 66 kilograms. And these are weight earths. So it actually excavates more than its mass, which is pretty noteworthy considering that I don't think there's any excavation device ever to do that. So Razer gives us this capability that can now excavate the soil and deliver it to this processing plant so that we can do that. But it also gives us a lot more. If you start to think about the whole architecture of like a mission, like I said, we're not just looking for water. We're looking for all kinds of other things. We can use just the soil to make protection berms for landing pads. We can clear roads. We can level areas. We can even use the soil and pile it on top of a habitat, because we've actually proven you can actually use the soil as radiation protection. So if you cover a habitat with soil, it actually is a great radiation protection. So now you can use Razer to actually collect the soil, cover habitats, and you get some things for free. Actually, it's kind of interesting. You can actually excavate the soil, deliver it to the processing plant. The processing plant separates rocks and all kinds of other things, and then spits out the stuff it doesn't want on the side. Razer can then go pick up the waste of that and then use that to go feed it into other systems, right? So the cool part about that is you filtered out some of the rocks. Now we have a filtered material. You could use that for 3D printing, and so that's some of the other work that we do. Razer would still be used as a delivery to a 3D print system, but we're looking at 3D printing on the Moon and Mars with local resources. And so that's another in-situ resource utilization, right? So we are collecting the local resources and using them to print things on the surface. And so initially these things are like, we could print structures, we could print habitats, you could print a road, you could print all kinds of different things. At some point we want to continue on and actually print parts, tools, all kinds of different stuff. But right now, the work we're specifically doing in Swampworks is we're actually printing structures. And what we're printing out of is actually the local material, where we have a basalt type material, which is a lunar soil, and we're mixing that lunar soil with plastic, and we're able to print structures. We've printed we actually printed a podium, just for fun. So in the podium in our Swampworks area is a podium. But we actually printed useful structures, like we've printed a barrier wall. And we're leading up to printing a full-on habitat. So what's cool about that is only 30% of the material is actually the plastic. So 70% is just the local soil we picked up off the ground, and you can then print with it. And so where do we get the plastic? So that's kind of an interesting story, is we can use the recycled plastics from the mission. There's leftover plastics on the lander. There's waste from the astronauts that you can use to make plastics, or even just plastic itself. On Mars, there's actually a process where you can actually collect the soil and the right minerals, and you can actually make a plastic on Mars locally. So we actually, on Mars, could completely not bring anything with us except for the actual processing tools, and we can make plastics and print the plastics and 3D structures on Mars. On the Moon, you'd have to bring the plastic with you. And so those are some of the technologies we're doing right now. And then even further from that, we've actually even proven you can not even bring plastic. You can pick up the local soils and you can heat them up and you can sinter them, which means you melt them to a point where they're not fully melted, but they just get partially melted around the outsides of the particles, and the particles stick together. We've made bricks, we've made lots of different structures, and so we actually made bricks that interlock, and you can lay them out on a landing pad, and we actually robotically deployed a whole landing pad made out of just sintered bricks, has no additives, just local soil, and we made it made these bricks. So now you've stabilized the surface for when the landers come in. And where that's important is when you start thinking about the architecture of a base. When a lander comes and lands, if there's nothing there, nobody cares. It just lands as everyone's happy. But now imagine you have a base on the surface right there, and you start to land your lander, and then the base is now just getting sprayed with all of the plume exhaust and dust from your lander. So the two things you can do: you can land the lander further away, and now you have to come to your base, or you land close, and you could make these landing pads to protect your base. But there actually has been proof to show that it's even worse than that. On Mars, when you land on a large human scale lander, there's actually issues of the actual jet from the rockets burying and digging holes as you land that could be big enough where the lander would actually fall into its own hole as it landed. So and in some cases, you actually have to do stabilization. You have to create a base for the lander to land. So that has a lot of these challenges, and we're only one part in NASA that's working on this ISRU technologies. There's Johnson Space Center and JPL and Glenn Research and others. Almost every center has their own little part of this, and we all actually are working as a pretty good team to collaboratively tackle this goal. So we hope in the next 10, 15 years we're able to start doing missions where we're proving out ISRU technologies as precursor missions, and then when we actually do a mission where we're bringing humans to Mars, we'll be able to implement these actual ISRU technologies on the surface. So I can take questions if anyone wants to ask any questions. So yeah, I'm gonna see if I can walk around with this. So
these tools, would they be managed from here, or would they be on?
Yeah, so in some of the goals, so something like Razer, it's meant to operate all the time. It kind of diverges from normal NASA rovers that are like science missions. It's meant to just operate and dig 24/7 kind of thing, So it would have to be fully autonomous or semi-autonomous. Okay, I guess I cut out there for a second. So the goal is to make it fully autonomous. On the moon, you can do some teleoperation driving because the time delay is not so great that you couldn't do some. On the Mars, with the large time delay, you pretty much can't drive those remotely. You'd have to be fully autonomous. And so the goal is actually to do that. And Kurt Lloyd is actually the software developer for Razer, and he's actually worked on some of the automation tasks. And it's not fully fledged at this point, but he has Razer currently driving in the bin, doing excavation and dumping in an automated fashion. So we're working towards those goals, and we have some future projects that continue working that. But yeah, that is the plan. So, any other questions?
Have you considered, in the spirit of the competition, to create multiple Razors to work together?
Yes, and that actually ties into this as well too. It's not just for prospecting. Yeah, it's not just for prospecting. You go and prospect, and then an idea is where you're going to swarm. You're going to go use the swarm to find your materials. But you can also use the swarming for the collection and excavation of the soils as well. So yes, as part of the architecture, that's part of the prospecting issue too. You don't know how much resources are there. So you get there and you're expecting 15% water, right? And so if you only bring one Razer, 15% is great, and you got enough resources, you're fine. But say there's only 5% water when you get there. Now you need more than one Razer to do the same task. So depending on what we think the actual resources there, how far the resources are away from where you land, you would need multiple robots to go out and collect the resources and be able to, and then also add redundancy, right? So completely, these ideas of swarming and things like that are stuff we're looking at and do expect, and the current plan for Razer is to have multiple of the robots. So.
What about the dust? So you're gonna be digging with dust, right?
Yeah, it's terrible.
This is a machine, so what are you gonna do about that?
Yeah, so we currently deal with traditional methods like we do on our seals and other things like that, which aren't really gonna work in vacuum and on Moon and Mars. And so dust is a huge problem. Our excavation robot currently in the bin just gets itself dirty all the time. As it's working and operating, it covers itself in dirt. Camera lenses get covered in dirt. It is a huge risk and a problem for the mission. And we've done some research into that, but it's still we still need to do a lot more. We have an electrostatics group in SwampWorks that has technologies where they can use electrostatics to levitate the dust, to remove the dust. We've looked at some of those things. And then as far as joints and other things like that, there's lots of different methods to seal rotary joints and things like that in vacuum. With shaft seals, labyrinth seals, all kinds of different methods. They're not perfect, and they are a challenge especially for a robot like this. It's even worse than just mechanisms. We're gonna have to have radiators on the robot, and the radiators won't work. They're covered in dust, and so the whole top of our robot potentially could get covered. And so you have to be able to keep those surfaces clean. The way we tackle some of that with our robot is because I mentioned the two drums are mounted on an arm, and the arm can actually flip the robot over. And so we've actually talked and looked into some ideas that since we're so mobile and we can do things like that, we'd actually stand up on our side using our arms to prop ourselves up. We can kind of knock some of the dust off and put ourselves back over again and keep going. So we have some, they're not foolproof, but we have some initial ideas of how we can try to manage and control dust. So it's not all the way there yet. Future research topic, if anyone's interested. Dust is a huge concern. And actually the lunar soil is terrible. It's crushed basalt, it's been crushed through micrometeor impacts over the whole history of the moon. So the particles on the moon are not rounded like beach sand. They're these jagged, terrible, rough particles, and they rip through everything. So
is this kind of like inspired by, I think they call it a von Neumann probe, where it just kind of goes and expands by itself, because it keeps creating more of itself.
Like self-replicating kind of things. Yeah.
So can you repeat the question real quick?
Yeah. So the idea was kind of, I don't know the term of the von Neumann probe, but it's essentially self-replicating deployed structure, like infrastructures and things like that, where you would send something that just continues to build upon itself. And I think that's everyone's goal would be able to do that. I mean, like we want to be able to go there. Maybe not full self-replicating. It could be in the realm, but the idea that you're going there, because that has other connotations. But you go there and you're going to build things all the way down to, you could build a rover, replacement parts for rovers, build everything you need for a base to support itself. And I was actually just at a conference recently, and there was a presentation talking exactly what you're talking about. He was talking about building circuitry and vacuum tubes and all these interesting things. And I think they are in the realm of possibility. It's going to start with some initial things that we're talking about, where you're going to find water, find the resources. But as you get smarter and you build more infrastructure, you can start making plants that are extracting everything, all the mineralogy, the metals, and everything. And once you start doing that, robot arm and a 3D printer can build lots of things. And I think there is the potential to do this. And I think that would be something that would happen in the future. But that's all part of ISRU.
So I've seen over the history of rovers and robots like that, I've never heard of anybody say, let's build a wrench monkey. Let's build a robot that's going to support robots.
Right.
You're going to build it exactly to be tough and full of tools and the right stuff. Have you thought about something like this?
Yeah, so I actually think Razer is kind of a first version of that. It's the first robot that is meant to work on a very strict schedule. Doesn't have science equipment, right? Doesn't have sensitive tools. It's meant to roll over. As I mentioned, the arms can lift itself up. It can climb over obstacles. It can dig. It can excavate. But it's very specifically built to excavation. It's not for building or repairing other robots. But it is that next step into, something a little more robust. And that is a huge problem going forward. Is how do you service these vehicles? How do you keep them running? We're all far away. The Razer mission could be up to a 5-year mission without any maintenance. That's a huge topic of is that even possible? And so going forward, there has been talk into that, and I know even at Kennedy Space Center, for even some of the launch pads and services that we have here, people have proposed ideas of robotic repair in some hazardous areas and things like that. And I don't think it's completely there as far as everyone's got the idea, but I know it's been proposed and it is an interest. And where we're kind of looking at it as now is we should look at 3D printing technologies so we can make replacement parts, but how you actually pick up those parts and install them. Right now, it would be the idea that in between crew missions, the crew would come and repair parts with locally sourced and created parts, but taking the next step would be to actually have robots install them. And I will say that on station right now they have Robonaut, which is the humanoid robot that's on space station that JSC created, and they do use it to do maintenance tasks on space station already. They have it. Some of these aspects, they even have it wiping down handrails and things like that. But they're leading up to where it's a fully articulated hand. It could do all kinds of tasks and work with tools. So there is stuff out there that could be gone into that arena, but I definitely know it is a topic of research. So.